Hello, my name is Victoria Ferdes. I work at Cisco on a product called Cisco NSO. Today I'm going to present you my latest work, which is in scope of software security. Software security is a critical topic. As we see, the threat level is increasing. Cisco published an annual cybersecurity report where they showed that the total volume of cybercrime events has increased almost fourfold in nearly 2 years. And the FBI published recently yet another report where they showed that there was an increase of more than 300,000 complaints of suspected internet crime from 2019 to 2020, which means that the threat level keeps on increasing. And therefore, one may say that programmers must have a security-aware mindset, and they must ensure that they deliver secure software. Well, it is easier said than done. The area has received great interest in the last years. Methods and tools have been developed. Take an example of the Cisco Secure Development Lifecycle. It is a software development methodology that underlines security at every stage of the project. It starts from day zero, when you're even only thinking about the project. And of course, there are tools. One example are the security checkers. Security checkers are tools that use static analysis to identify security vulnerabilities. For instance, remote code execution, buffer overflow. Security checkers can start from a point where a non-trustworthy input enters the system. And then they are going to follow the data and report if the data is manipulated by the program in a way that can be exploited by the attackers. There are security checkers for Erlang as well. There is PAST, which is the oldest and reports a lot of false positives as it doesn't use data flow analysis. There is a trojan analyzer and another security checker built into Refactor. Both of them are based on data flow analysis. So there are even tools for Erlang. So we could say that there are methods and tools to help the programmers. However, there is a catch. Brittany and her colleagues published a survey in 2013 where they point out that developers are not using security checkers. One of the biggest reasons are because of the existence of the false positives. And well, if you think about it, this is understandable. Just imagine you have a project containing millions of lines of code. The security checker returns, let's say, 100 results. You sit down, you start analyzing the results, and you become disappointed. None of the results are valuable or relevant. They are mostly false positives. So you feel it is a waste of your time, and you stop analyzing the results. You stop using the tool. I consider this as a problem, and I would like to make the situation better. I observed that there is no Erlang specific security checker that underlines the most critical vulnerabilities. And I wanted to fix that. So my goal is to provide a security checker that shows the most critical vulnerabilities first, so the programmers don't get disappointed. Let's talk about security flows a bit. In real-life projects, modules belong to multiple logical groups. A group of modules solving a specific problem using the same privilege level can be considered as a trust zone. These modules can interact with each other freely, they can trust each other and the other's data. In real life, we are not going to validate data in every module, right? So modules belonging to one trust zone, they trust each other and the other's data. Therefore, there is no need for data control. However, data that is entering the zone should not be trusted and needs to be validated. Hence, our focus is on the boundaries where the system is most vulnerable. And what is the goal? To validate or sanitize data entering the zone. We want to avoid situations where data entering a trust zone through one of its entry points and flowing into a high-risk vulnerability without any sanitization. Now let me give you a longer example. So let's say we have a component in our system that is responsible for user handling. And whenever a user arrives, it is going to perform some initialization. As part of the initialization process, the component is going to load the user cache to memory, ensure that the workspace of the user on the file system is present, and starts user processes. And the ensure user.dir function is implemented as follows. Take the username given as input and ensure that the directory named after the user exists in the root directory. We know how to do this in Unix, and of course we know about OS command. So the implementation of this function becomes calling OS command with a prepared string. If the user is the wiki string, this works as expected. If the user is a hello atom, then well, it's going to crash. Fine. But if the user is the following string, semicolon rm-rf/, then something terrible is going to happen. So what's going to happen is that we are going to execute a command that attempts to delete the whole root directory. So we have discussed a bit the security flaws that are in focus right now for the paper, but the next question is, what makes a security flaw critical? The example I gave you is a critical vulnerability. However, the altered code I show on the right side of the slide would be considered by a programmer not critical or false positive. Why? As you can see there, we first check if the user exists. So there is some sanitization, validation of the incoming data. And only if that user exists, then we are going to continue with initialization. In summary, we can say that criticality depends on whether there is input validation or sanitization of the incoming data. Alright, so to prioritize vulnerabilities, we need to be able to recognize input validation in Erlang. How can we do that? There is a language construct in Erlang called patterns that allows us to test the structure of a given value. Examples are check and the check2 functions. However, notice that check3 is not really a good input validation, right? It uses the Joker pattern, and that does not put any constraint on the expression. The second and last language element we have are the guards. Here again, we need to ensure that the test is meaningful. So a guard that is only a type test should not be considered as input validation. Now we know how to recognize input validation in Erlang. So now we can discuss the prioritization problem. So our goal is to prioritize vulnerabilities where an incoming data flows into a vulnerable function of Erlang OTP without any non-trivial input validation or sanitization. If you think about it, those are the most critical ones, because it means that whatever a trust zone is going to receive, it is going to reach the vulnerable function of Erlang OTP. So this gives a possibility to exploit our code by the attackers. In the analysis, we are going to use higher order data flow analysis for multiple reasons, but we are going to use it to see if an incoming data reaches a vulnerable function of Erlang OTP. That's the most important part. And we are going to use control flow analysis to ensure that and the execution passes between the entry point and the vulnerable function of Erlang OTP, there is input validation, and it is towards the entry expression. The algorithm that prioritizes the found vulnerabilities is as follows. We take as input triplets, each of them representing one vulnerability. So in the triplets, we are going to have a source, and that's where the data entered. That's the entry expression. We are going to have the sink, which is the reached vulnerable function of Erlang OTP. And we are also going to get the read set of the source calculated by higher order data flow analysis. The output of the algorithm are the source sink pairs tagged with severity. Okay, the algorithm goes as follows. Now later I will show you examples. But let's go through the algorithm first. So we are going to start from the sink, and we are going to perform a backward search on the execution path provided by the control flow analysis. We need to be careful with branchings because we need to explore all possible execution paths. Now, to narrow down the problem space, we are going to use the data flows read set to prune the execution paths, skipping the part which is independent from a source. So, for instance, if in the execution path there is a function invocation where we do not pass the value of the entry expression, that function we are not going to explore. There is no need for that. All right. Now, at every step of the walk, we are working with one Erlang expression from the execution path. And what we are going to do with that Erlang expression is that we are going to check if it is a relevant, non-trivial input validation. So it is relevant if the input validation is against the entry expression. So if we find an input validation that is against some other value, then well, our entry expression has still not been validated. Then we need to see that the input validation is meaningful from a security point of view. So if it is a pattern, but it is the Joker pattern, then we are not going to consider it as input validation, and the same holds for type tests guards as well. All right, so if we do this check on every Erlang expression that is in the relevant part of the execution path, and we walk backwards on the execution path. And if we reach the source in any of the execution paths without finding relevant input validation, then we have found a critical vulnerability, because then we discovered an execution path where the incoming data flows into the vulnerable function of Erlang OTP without any input validation or sanitization. If we do find relevant, non-trivial input validation on all the execution paths, then we are going to mark it as warning only, the severity. Yeah, observe that we do not drop found vulnerabilities. I'm on the opinion that this is only a heuristic and it may down prioritize vulnerabilities. So what I would like to have is to be sure that the very critical ones are marked with critical, and the very critical ones are the ones where there was absolutely no input validation towards the entry expression. and that the algorithm does. So this way I can be sure that I will put those ones as the first one. And then I will have the programmer engaged, basically. Alright, so let me show you how the algorithm works. In this example, A is the entry expression, and the reach vulnerability is OS command. So we start from OS command, and we walk backwards on the execution path. So first we get to the true pattern, and well, we see that this is not against the value of A. So we continue. Now we check the bar B function. However, we see that bar B function does not take the value of A, so it is irrelevant from our point of view, so we can skip that. And then we reach to the head of the F function, where we again don't see any input validation against A. So we can conclude that this example is a critical severity, as we did not find any input validation against A before it reached OS command. Now let's see another example when the severity will be only warning. Again, A holds the value of an entry expression, and we start from OS command. We are going to do again the backward search on the execution path provided by control flow. We check true, it is not against A, we keep going, we don't explore the bar function, as we see based on data flow that it does not take the value of the entry expression as input. So we keep going on the execution path backward. Again, this true pattern is not against A, and then we are going to reach the foo function. And based on data flow analysis, we can see that this invocation of the foo function takes A as input. So we are going to explore the function definition of the foo function. We start from here. We see that there is a false atom. This is not an input validation of A. So we go to the function head, where we find a pattern, and we know based on data flow that this is against A, but it is a joker pattern, so this is not this is a trivial input validation that we don't accept. So we keep going. We find again now a true atom, which is not an input validation against A. So we keep going, and now we find a pattern which is a non-trivial pattern, and it is relevant because based on data flow analysis we know that the value of A is going to reach here. So we conclude that we have found input validation on this execution path. So on this execution path we have found input validation of A. As this is the only relevant execution path, this is the only one that we are going to explore, and we are going to conclude that that this is only a warning severity. It is a warning severity because the incoming data was first validated before it reached OS command. The prioritization algorithm I've showed you is now part of the trojan analyzer algorithm. So the extended trojan analyzer takes as input a trojan with its entry expression, the sources, and it's going to output the source sync pairs tagged with warning or critical severity. The algorithm has three phases. The first phase is the initial analysis, which is purely based on data flow, and it is going to find all possible vulnerabilities. The second phase is the prioritization algorithm I showed you, and the third phase is ordering the results based on severity and presenting it to the programmer. I created a prototype implementation of the extended trojan analyzer, and it is available on my GitHub. You can download it, try it out, and use it. Today I showed you my latest work that I really hope will be used by the programmers. It underlines critical vulnerabilities where untrusted data reaches a vulnerable function of Erlang OTP without any input validation or sanitization. Early results show that the algorithm works and adds only acceptable overhead. Like I tested it with React Core, that was my trust zone, and it added the prioritization added around 2% to the runtime. I'm planning to continue its evaluation and want to see how it performs on more test subjects. Thank you for listening.